Okay, I want to start by thanking the organizers for giving me a chance to reflect some of the work going on in my lab here. I'm speaking on behalf of many of us listed on the slide here. I want to start by echoing some of the points you heard earlier, that really, if you think about any science, the point of a good science is to take measurements in some domain 1 and make accurate general predictions across this accurately into some domain 2. For many of us here, that first domain is the domain of images, and our goal originally was to try to predict things about behavior and perception. This is why we're at VSS. So the accuracy of this predictive mapping is a measure of the strength of any scientific field. I think you heard that implied in the other talks. And this accurate predictivity, we think ultimately is what the reason we're doing science, the ability to build, fix, or augment systems, in our case the visual system. So there's been, this is of course classically the domain of psychophysics, and there's been some great success stories here, but things became challenging when you get to complex tasks, things that we like to work on, things like object recognition, that this mapping is very hard to do. And for that reason, and for other reasons, we went inside the system, and there was a big rush in the field to start going inside the box, so to speak, and measuring neural activity. So here each of these dots might refer to, say, the spiking pattern of all neurons in a particular area. And I think that's what people are here loosely referring to as, quote, neural representation. And with this movement came, as you saw in all those talks, certainly most of what you've seen already is a focus on mapping between images of neural activity and trying to build good predictive models there. And while we think that's important work, and we do that kind of work ourselves, as I'll show you, those are called encoding algorithms, we think that this sort of history has caused us as a field to essentially been neglecting this link between neural activity and complex behavior and perception. Behavior and perception is not image reconstruction. It's doing much more than that, and I think you heard that in many of the questions. So this link has been neglected, and it's been dominated by weakly predictive word models. In my field, those go something like, IT does object recognition, let's go home. Face neurons do face tasks, let's go home. And my personal favorite, attention solves that. So we now have to try to work, and what many of us want to do is to actually build accurate decoding algorithms that go from neural activity to behavior and perception. So we don't think of this as just extracting activity from the brain. We're trying to build mechanisms that go from this to these things that we can measure behaviorally. Okay, and this is important. This accurate decoding link is important because, remember, behavior is the reason that we're here. It's the reason the public pays us to be doing this kind of work. This is why they're interested in this and why we're studying neurons and not liver cells. This is why, say, we focus, gets us focused on encoding algorithm efforts that on the aspects of activity that actually matter, that are relevant to behavior. And it prevents any work on encoding algorithms from devolving into just trying to produce fits in limited domains, say, for instance, white noise images. Okay, so my lab works on a particular subdomain of vision, object recognition, and by that I include faces. When we do recognition, of course, primates don't absorb a whole scene like this. We digest the central 10 degrees. We do this by making rapid eye movements across the scene, sampling the scene in 200 millisecond fixation intervals. And what that does is bring to our ventral stream engine something that looks like this, a series of snapshots. You can notice that you can recognize one or more objects in each and every one of those images. This ability we call core recognition, as described here. I like to illustrate how good we are at this by always showing this RSVP video. This was shown by folks like Molly and Potter in the 70s, that we can do this quite well, quickly mapped one or more objects in images like this. So this ability, core recognition, is not all of object recognition, but we think it's core to the process. And so that's everything I tell you today is focused on this behavioral ability, what we call core recognition. The reason core object recognition is hard, one reason is that there are many possible objects, tens of thousands of possible objects, and also that each object can produce an essential infinite number of images on the retina due to changes in things like position, size, pose, illumination. Okay, so the way then we study this is we actually just take 3D models. We have lots of them. We can control their latent parameters. We can then render them, and we can place them on backgrounds. We tend to place them on uncorrelated backgrounds to remove confounds that computer vision algorithms like to cheat on. So we end up with a bunch of images that look like this. This might seem strange to you that you have cars floating and heads floating, but this turns out to be a very powerful space that you can, challenging for computer vision, yet very doable by humans, and we think is tapping something that fundamentally our visual system is doing quite well. And it's a very generative space of parameterized images. Okay, so just to give you a feel for it, you know, we show images like this, 8 degrees center of gaze, 100 or 200 milliseconds, that doesn't much matter, you get similar results. You can sort of do this yourself. That's a car, that was a plane, that's a face. Car. Okay, you get the idea. It goes pretty quickly. It's very easy, even with those funny looking images. Okay, I want to point out that what we'd really like to do is characterize fully core object recognition. We haven't done that yet, but we've been working to characterize what we call basic level core object recognition among all basic level objects. And I'll point you to a talk by Ha Hong, a graduate student in the lab, on Tuesday, where we've characterized, we think we can contain all essentially 10,000 objects in a compact space of somewhere between 20 and 50 dimensions, and Ha will tell you the data to support that idea, and we think that's quite cool. So please go to that talk. What I'm going to tell you about is a sample of core object recognition space that we've done in the past, where we sampled tasks like these kind of objects shown here. So it's not, again, a full characterization, but just a sample so that we can measure some behavior within this domain, that we have a target to ask about the link between neural activity and behavior. Here are the kind of data you get out when you measure humans' ability to do these kind of tasks. For instance, discriminate animals from other basic level objects, or Astras from other cars, or face one from a bunch of other faces. Here's showing the amount of variation that we put in and how much view, pose, and so forth variation we have in the objects. And you can see from the D prime values that as you add more variation, it generally gets harder, and this isn't surprising. You should notice that humans aren't perfect at everything. There's a wide range of D primes, and some tasks are harder than others. This is not something that is noise. This is a pattern of performance is reliably explained, reliably produced across different human observers, and you might intuit that this, of course we should get data that looks like this, but again, you're doing intuitive psychophysics when you make those estimates of saying, oh, these are harder than that. This pattern is not easily explained by low-level visual features, as he'll tell you in a moment. Of course, your brain sort of perceives that this is hard and this is easy, but this is not easily explained by low-level visual features, and that's what we're after. Okay, so would like to study this brain, the human brain. We study this brain, the non-human primate. You might say, well, monkeys can't do recognition. Well, that's not true. I refer you to a poster here by Rishi Rajalingam in the lab. These show confusion matrices that he's collected on humans and monkeys. You see how very similar they are in basic level recognition tasks. So once you train monkeys to do these kind of tasks, they make essentially the same patterns of errors as humans make. So this is a very good behavioral model, as we suspected, and here he's showing it directly. So now, because these are monkeys, we know a whole lot about their ventral stream, as you've already heard about. We study this area IT, especially in its precursor area V4. To remind you, IT projects to regions involved in decision and action and to regions involved in memory. We can study these representations because they're monkeys and not humans at the level of neuronal spiking activity, and that's what we do. Okay, so we lay out the representations shown here as a series of population representations. Each is a retinotopic map, as you know, well know in this audience. In this symposium, I think we're all thinking of each area as conveying a new population representation. So when you watch that RSVP video, there's neurons in your various visual areas clicking along, learning something schematically like this. Remember, our goal is to understand the link between neural activity and behavioral report. That is, what aspects of this neural activity explain behavioral report, and exactly how does it do so? This was one of our goals. This, again, is what we would call a predictive decoding algorithm. This is work done by Najib Majaz when he was a postdoc in the lab, Ha Hong, a current graduate student, and Ethan Solomon, an undergraduate. We did this work by recording from multiple areas along the ventral stream using chronic recording arrays, so we can record hundreds of neural sites simultaneously, and we pool this across various monkeys. I won't have time to tell you about the details of our data, but just for those of you who haven't seen IT data, these are spiking data from IT. Each tick mark is an action potential. These are different sites to a set of very simplistic images shown here, just to give you a sense of it. And you can see that different sites respond to different images, and you can also notice that there's this sort of response window that IT neurons tend to respond. We've narrowed down a key response window, as I'll show you in a moment, that seems very relevant to behavior, as highlighted here in yellow. And you can also notice trial-to-trial variability that any decoding algorithm has to deal with. Okay, so what I want to tell you, the top line on this part of the story, is that we can now use a predictive population decoding methods. We can now, using those methods, we can now report a decoding algorithm that accurately predicts behavior. And so let me tell you in outline what that algorithm is. The algorithm samples from approximately 150 arbitrary sites spatially distributed over all of IT. It measures each site average spiking response, average over 100 milliseconds, in that sort of in that window I showed you a moment ago. For each object that you want to be able to discriminate, it learns an appropriate weighted sum of those 100 measurements. If you want to boil this down into a phrase, it's a learned weighted sum of approximately 150 distributed average over 100 millisecond responses in IT. That's still too long for me, so I boiled it down into this little acronym, Laws of Dark IT Algorithm. Okay, so I'll refer to all of this as Laws of Dark IT Algorithm. So here is my evidence that some of the evidence that this algorithm is actually a predictive and decoding model. Here's actual behavioral performance measurements that I showed you earlier with some tasks indicated here. So here's D primes ranging from 0 to 6. Here's the predicted behavioral performance of this algorithm, again, reading IT data to make these predictions, again, over 64 tests. You can see this is very close to the unity line, predicting both the pattern of difficulty of the task and the absolute magnitude of performance of these tasks. I want to say as a sidelight last, in cosine this year, it's not just category that can be predicted. You can also predict very accurately other variables, and we think to human level, the ability to estimate position with this exact same algorithm can estimate position of an object in an image like this. And that's work that we presented in cosine. So for those of the neuroscientists in the room, this may sound, again, like a computer algorithm, still a little too disconnected from the brain. The way to think about this is that you have IT cortex. Think about downstream neurons in areas like prefrontal cortex or perirhinal cortex. They need to sample from this. And at the end, after all this is done, what they're really doing is, we estimate, weighting approximately 5,000 single unit inputs to a neuron. And if you wanted this simple model to then produce, say, a face, or responding to say, I see a face, I see a car. So there's a mechanistic implementation of this. If you're interested as to why this is 5,000 and not 150, I'm happy to answer that in questions. Okay, the result that I pointed out here is non-trivial. Most alternative algorithms cannot predict the behavior I showed you nearly at all. Here's the laws of our dark IT algorithm that I described. Here's its accuracy of prediction, now quantified here. It's within the human-to-human consistency, similar to Nico's talk. You're in this gray bar. That means we cannot distinguish the output of this algorithm from another human being. Other ways of reading IT or other visual representations like V4 or simulated V1 or some computer vision algorithms don't come close to this. That does not mean that these areas are not somehow involved in recognition. It just means that we don't have a predictive decoding algorithm that goes from them to these kind of behaviors. Okay, it also can predict reasonably well the patterns of confusion matrices shown here. Again, the different confusing one object for another, not just performance. Here's a noise-corrected correlation. Although this is not quite as accurate currently at these higher levels of variation. That's something that we're still trying to understand. Okay, so we have a very good, though still not perfect, decoding algorithm that goes from IT into producing the behavioral report, again, quite accurately. Why should we care? How can this kind of algorithm actually help the field? Well, I want to say that, first of all, it predicts that changes in behavioral report resulting from manipulations of neural activity can be predicted from this kind of algorithm. So for instance, it tells us if we manipulate IT neurons, say by turning them on and off with light, optogenetics, that might have value for brain-machine interfaces, it would tell us what should happen in behavior. So it gives us prediction. And if we bend them with learning, it tells us what should happen. If you're interested in our optogenetics work in IT, I refer you to this talk here on Sunday by Arasha Fraz. Also, it tells us what aspects of IT activity must actually be explained by these bottom-up encoding algorithms. It grounds these kind of algorithms, and we think that's important. In some sense, it helps define what the IT neural representation is, at least with respect to tasks like core object recognition. Okay, so where I've taken you so far is I've given you a predictive model that goes, we think, reasonably well, and I'm showing these as dotted lines because it's not perfect yet, but it's very, very good, between IT neural activity and behavior and perceptual report. And it's a predictive model over this entire domain. Now, what I want to tell you about in the last few minutes I have left, and Kendrick, please interrupt me when I run out of time, is the encoding algorithm. Again, I mentioned we're not just interested in this, we're using this partly as a constraint on this, the encoding algorithms that takes us from images to IT responses, similar as you heard in many of the other talks. So I'll briefly tell you about our work on that line here. We've been using a large class of these kind of convolutional networks. These are similar to things you've already heard about. The things I want to highlight for those of you who aren't used to these kinds of algorithms is that they have elements that we would call neurons that have large fan-in, they're filters, they have simple nonlinearities that are similar to the known visual system. Each layer is convolutional, as I mentioned. That, if you don't know what that means, just think of it as emulating retinopathy. It has many types of tuning functions. So for instance, at the first layer, you could have many different orientations of Gabors. That's what the stack indicates. And there's a deep stack of layers. Here's shown 3 layers. In the model I'll tell you about, we have 4 layers. Okay, so what's good about these algorithms is that they're general and predictive. As you heard from many other of the speakers, to any image it will predict what neurons should be doing in each of these different layers. So these aren't word models, they're real algorithms. But the problem is this is a very broad class. There are many, many, many thousands of unknown parameters that are not directly determined by the neurobiology. So how do we set those parameters to actually choose an algorithm? Well, this is work done by Dan Yeamans, a postdoc in the lab, and again, Ha Hong, a graduate student, and what they wanted to do was to better mine this large class of algorithms for ones that might be better explaining of the ventral stream, be a good encoding algorithm of the ventral stream. So to do this, we thought we'd use optimization methods to find specific algorithms, find parameter methods, and what we were going to optimize was not fitting neural data, but to optimize the kind of visual tasks that the laws of dark IT had suggested the ventral stream was actually built to solve, the kind of tasks I showed you a moment ago. We think of this optimization as being akin to perhaps an evolution or developmental process, and we're agnostic about which aspect that is. This is the big picture of what they did. Here's the kind of tasks, again, that they were optimizing towards. They're very similar to what I showed you earlier. You have 3D objects. You have a large number of them. They have semantic breadth. You're going to render them with large amounts of variation. And these are just some example images. Again, background correlations, making backgrounds completely uncorrelated. To show you when we optimize this way, here's the first algorithm that came out. This is 2012. This is we called it the Hmo algorithm, which stands for the type of optimization procedure. That's a detail that doesn't much matter to us, but if you care about the details of this, I refer you to the paper that's just been published. So it shows that the algorithm performs well on these kind of tasks that other algorithms hadn't been performing well on. So that said, it was kind of in the game. And then what we did is take the model. So here's the model laid out. It's a 4-layer model of that class I showed you. It has specific parameters now all set. We'd optimized it to do these kind of tasks up here. And now what we did was to ask, how well is it going to explain IT neurons or V4 neurons? So first we did, to fit IT, we took the top layers of this model and just did linear regression. And so this is analogous to what Nico had just told you, that we need to now is we need to map this onto IT. So what we do is we take some of the data to fit the linear mapping, and we test how well it fits on the remaining part of the data. So we're asking if this linear basis, if this is linear, this is like a rotation of that. And there are RDM ways of doing this that we've done as well, and I'd be happy to talk about that. But here's the single unit data for those of you who like single units. The black line is the response to hundreds of images. This isn't time, these are images, and they just happen to be grouped by categories here. There's images of the type I showed you earlier, the one seen here. The red line overlaid is the prediction of the Hmo algorithm for this particular neural site. I want to remind you that all of these images, the predictions, this is predictive. None of these images were previously seen by this Hmo model in making these predictions here. You can see it does a pretty good job, R squared of 0.48. That is really, really good for IT. Here's another site, just to flip through it. You might have called this a face neuron in a simple way. You can see there's still structure within the category of faces, and it seems to capture that somehow. Okay, so it also fits other neurons that you can't easily call as category selective in some simple way. It seems to capture their responses as well. And so on average, what you get out of the top layer of this algorithm is about half of the response variance on average is explained, half of the explainable response variance. And that's much better than all these previous other models as compared to down here. And this, again, a dramatic improvement over previous algorithms. So we also then went on and went to a next step and said, well, we're fitting IT pretty well. What happens at these intermediate levels? Remember, these algorithms had never been optimized to do any kind of neural fitting. They were optimized to do this kind of task, but they had a structure like the ventral stream. So then we go in and look at the middle layers, and this is V4. Now looking at goodness of fit of V4 neurons, that's on the y-axis. Here's the model predictions, or the fits of the model, done in exactly the same way as we did for IT. And what you see is the intermediate levels of this model predict about half of the response variance in V4. And again, we find that quite remarkable because all that we're really done here is we took a bio-inspired algorithm class plus a set of tasks that we thought we'd chosen in the right way and just an optimization method, and it produced neural-like encoding functions. It produced what appears to be a very good encoding algorithm. And I want to just sort of give you a big picture of what this means or how we think about this. So one thing that we noticed is that anytime these little dots indicate individual encoding algorithms, those are a set of all those parameters in any one of those models. So you see lots of dots there, and these black dots are specific models that are in the literature. So what's on this axis here is performance of those algorithms on those kind of recognition tasks that I've been showing you, high variance core object recognition tasks. And this on the y-axis is the ability to predict IT neuronal responses, as I described in the last few slides. So what we did was we saw this plot and we said, look, there's a correlation here, so if we can optimize for this, that means that we might get a good high-performing model, which we did, and then it turned out that it's just continued to follow this trend, that it actually still is explaining the IT responses even better. So you don't have to be a rocket scientist to say, well, keep doing more of that, and you might be getting more of that. And that's essentially where we're headed. So what I've told you now is that we've now built predictive models that go from this domain in IT to this domain. I called it the laws of dark IT decoding algorithm. There's still work to be done. As I mentioned, it's not perfect. I haven't shown you predictions for each image, and we think that will be interesting to pursue that line and further refine these decoding algorithms. This is not the end of the game, it's the beginning. I also I told you about the Hmo encoding algorithm. That, as you saw, is half the variance explained, but still work to be done. And so we're working on that as well. And we'd really like to see if we can make that unsupervised, and that's the kind of active work that's going on in the lab. So just for my end here, I want to give you my answers to the questions that the organizers asked me to put up here. What is the most critical open question about visual representation? Well, I hope you heard in my talk here that what we need to do is to have accurate predictive maps from neural activity to behavior and perception, call those decoding algorithms. That doesn't mean we don't need encoding algorithms, but this has been relatively neglected and I think really sets context for those encoding algorithms. Again, they tell us what aspects of neural activity must be accurately predicted from visual images, and also which details, if you will, about neural responses are not actually critical with respect to the behaviors that we define to be interesting. And it focuses those encoding efforts also on the full domain of task-relevant images, again, rather than going into a subdomain of images. And as a bonus, we think this is also itself deeply interesting and has direct applications. For instance, brain-machine interface, manipulating those neurons directly to induce perception. So to achieve this goal, what is the most important thing we need more of? Well, we just need efforts to build these kind of algorithms. We need to go away from word models, and these predictive algorithms need to accurately link neural activity to behavior and perception. To do that, I think hopefully many of you in the room will like to hear this. That means we need rich characterization of domains of visual behavior and perception. That means we need more good psychophysics in these domains. That's the target that we should be aiming for. These kind of models need those kind of data and that characterization in both humans and animals. And so that's the thing I would say we need the most of at the moment. I want to thank these folks who did all the work here, especially Dan Yeamans and Ha Hong, who I mentioned throughout the talk, and also my funding agencies, and thank all of you for your time and putting up with my fire hose presentation. Thank you.